Good evening. It is an honor to present Professor VIJAYAKUMAR ANAND, who received his bachelor's and master's degrees in physics from the American College in 2004 and 2007, respectively. India, and Master of Technology in Laser and Electro-Optical Engineering from College of Engineering, Anna University in 2009. He was a Monbuka Kokso Fellow at Osaka University, Japan from 2010 and 2012. He obtained his PhD degree from the Indian Institute of Technology, Madras, India in 2015. He was a PBC Outstanding Postdoctoral Fellow at Ben Gurion University, Israel from 2015 and 2018. From 2019 to 2021, he was a Deputy Vice Chancellor, Research and Enterprise Fellow, Photonics Fellow at Swinburne University of Technology, Australia. He started his position as ERA CIPHR Chair and Associate Professor of Computational Imaging at University of Tartu, Estonia in 2022. He is also an adjunct associate professor at Optical Science Center, Swinburne University of Technology, Australia. He has published more than 100 journal articles, conference proceedings, and book chapters. He is also an author of a best-selling textbook on design and fabrication of diffractive optical elements with MATLAB, published by SPIE Press. He has been elected to the editorial board of Nature Spring, Applied Physics B, Laser and Optics, and Chinese Optics Letters. His current research interests include computational optics, imaging, digital holography, diffractive optics, and macrofabrication. Now I invite Professor VIJAYAKUMAR ANAND to start delivering his talk. Please, Professor.
Yeah. So, okay. So before I start my talk, so I would like to say a few things about Sir C.V. Raman. So Sir C.V. Raman seminar. So I watched this seminar by Professor Siddhartha Ramachandran a couple of days before. And his research work was actually very much connected to the webinar itself. So he presented on Raman scattering. And so this is actually a great initiative from Professor Sankara Raman, because it not only reminds us of the contributions of Sir C.V. Raman, but also encourages young minds to choose research as a career. And in my case, I also believe that there is a kind of a connection between Sir C.V. Raman and me, not in terms of the research area, but in terms of where I started my research career. So my research career actually began at Raman Research Institute. I was a bachelor student. I applied for this JNCSR summer research program, and I did my first supervised project with Professor Hema Ramachandran. And during that, these summer research programs are very good opportunities to grow. So I met with different, people. Some notable people are like Professor Jimmy Sebastian, Dr. Jinto, Professor Kamaraju. So interacting with them, helped me choose this research path or this career itself. And so some funny things about being in Raman Research Institute is that even though I was working with Professor Hema, most of the time I was in Professor Reggie Philip's lab. I think Professor Reggie Philip used to think, what he's doing, maybe he's interested in non-linear optics. But, I usually go there to play video games with Jimmy and Jinto, because he had the fastest computer at that time. So, yeah, it helped me to choose this research career. Not the video game part, but the interaction with Jimmy, Jinto, because they were from IIT Madras. I was just a bachelor student, and they helped me to, choose this path. So, okay, so there's a good connection. And once again, I thank you for giving me this opportunity. And my talk is on, say, finching objects with super resolution, fundamentals to application. This FINCH stands for Fresnel Incoherent Correlation Holography. This is one of the milestones in the history of holography. So let me start this. So this will be the outline of my presentation. So first I will explain some of the fundamental differences between imaging using coherent and spatially incoherent light. And coherent source, you probably know, they are like the laser-like sources, which are spatially and temporally coherent. This spatially incoherent light, they are from LEDs or even natural light. And after this, I will introduce the core concept, which is Fresnel incoherent correlation holography. I will talk about how it changed the field of imaging. And then I will introduce this concept of Lagrange invariant condition and how by breaking this condition you can achieve super resolving power. And then I will talk about the evolution of Finch during the years from its invention in 2007 until today. And then the applications and challenges in Finch technology and what are the solutions we have developed. And single camera shot Finch. Like any holography technique, Finch also requires multiple camera shots. So achieving a single shot holography itself is a significant step. So I will talk about that here. And finally, conclusion and future perspectives. Okay, so first, the differences between imaging with coherent and spatially incoherent light. Okay, so if I ask this question to a, say, undergrad student, so he would say this, coherent imaging system requires a laser, and incoherent imaging system requires, does not require laser. It can work with low-cost LEDs or even natural light. And the other important factors about using incoherent light is that they do not suffer from noises, imaging noises, like speckle noises, edge ringing effects, and finally, the modulation transfer function, MTF. The MTF of coherent imaging system is kind of narrow, whereas incoherent imaging system has a broader, almost twice the bandwidth of MTF of coherent light. Okay, and so we need to understand this point because the other three are quite clear, and the last point is very important. This is the starting point of super resolution. The bandwidth is high, so it is possible to improve the resolving power. And why this bandwidth is twice? It roots from a fundamental fact that a coherent imaging system is linear in complex amplitude, whereas an incoherent imaging system is linear in intensity. However, when we try to image a single point, you can see there is a single point here, and it creates a single point image. And this is true even for incoherent case. So when there is a single point, there is actually no difference between a coherent imaging system and an incoherent imaging system. However, when there is more than one point, so then the differences start showing up. So in order to explain this, so I would like to show you a video. This video is definitely not a scientific video, but I promise you that once you see this video, I don't think you will forget the difference between coherent and incoherent light. And at University of Tartu, we focus on teaching science in a very fun way. So I hope you will enjoy this video. And for conventional speakers and listeners, please excuse me. Okay, so it's a very short video. So okay.
Well, you fill in the blanks. Okay, so now.
Can you hear the video? See the video?
We're going to start discussing men's brains, women's brains, and how they're very different.
Okay.
Now, I want to start with men's brains. All right. Now, men's brains are very unique. Men's brains are made up of little boxes. And we have a box for everything. We've got a box for the car. We've got a box for the money. We've got a box for the job. We've got a box for you. We've got a box for the kids. We've got a box for your mother somewhere in the basement. We got boxes everywhere. And the rule is the boxes don't touch. When a man discusses a particular subject, we go to that particular box, we pull that box out, we open the box, we discuss only what is in that box. All right? And then we close the box and put it away, being very, very careful not to touch any other boxes. Sorry, my Catholic upbringing got in there for a minute, but I'm not a Catholic, but I went to Catholic school when I was little. I had a nun who taught on hell like she was born and raised there. I mean, I'll never forget it, but it did me good, actually. It was a good thing. Now, women's brains are very, very different from men's brains. Women's brains are made up of a big ball of wire. And everything is connected to everything. You know, money's connected to the car, and the car's connected to your job, and your kids are connected to your mother. It's like the internet superhighway. And it's all driven by energy that we call emotion.
Okay, so I hope you enjoyed this video. And so this is, video to discriminate between men's brain and women's brain. But, the men's brain, they are like, as per the comedian, so it is made up of boxes, and the boxes do not touch each other. So this kind of configuration is what is present in incoherent or spatially incoherent imaging systems. And the other brain, where every point is connected to every point, it's like a ball of a mesh. So that is actually coherent imaging system. So that's what I'm going to explain. So when there is more than one point, so in the case of coherent imaging system, you can see that there is interaction between light diffracted from one point and the light diffracted from the other point. Whereas in the case of incoherent imaging systems, the boxes don't touch each other, and so there is only intensity addition. And so when we try to image a complicated object like this, so in the case of coherent imaging system, you can see that because of these interactions, there is noise. There is this edge ringing noise, there is other kinds of noises, speckle noise, but here you can see it is very clean. So this is one of the reasons why scientists or optical scientists, we prefer using incoherent sources for imaging applications compared to coherent sources. Okay, so now let us try to understand this in a slightly more deeper way. So I mentioned two statements about coherent imaging system and incoherent imaging system. In the case of coherent imaging system, I mentioned that the system is linear in complex amplitude, whereas in the case of incoherent imaging system, the system is linear in intensity. So the same statements I have written in terms of equations. So this is the equation for imaging using coherent systems. So the small h, which you're seeing here, is the PSF, or the point spread function. And this u, it is the object function, complex amplitude function. And this convolution operation, as you saw in the previous figure, transfers this PSF to every point of this object. And since most of our sensors, or all of our sensors, cannot measure complex amplitude, but only intensity, so we take this modulus square. In the case of incoherent imaging system, you can see that the case is different because the linearity exists only in intensity. So what we have here is the modulus square of the PSF, which is the intensity of PSF, convolved with the object intensity pattern. And if we take Fourier transform on both sides for the two equations, when we take Fourier transform, convolution becomes product and product becomes convolution. So the small h becomes capital H, which is the modulation transfer function, which I was talking about. This capital G, it is the Fourier transform of the object. But here, in the case of incoherent imaging system, what we have here is capital H convolution capital H. Now we need to first understand what is G. So G, it actually tells us what are the spatial frequencies and how much of the spatial frequencies make this object. So if we transform this spatial information into spatial spectrum information, so then we get this information redistributed in terms of spatial frequencies. And this H, it acts as the filter. It decides how much of the spatial frequencies will enter the sensor. And so here, what we have is H multiplied to G, but here H convolution H multiplied to this. So what it does is like this. In the case of incoherent imaging system, you can see that the bandwidth is higher. So when we send a spatial frequency comb like this, so in the case of coherent imaging system, only part of the spatial frequencies enter. But here you can see more spatial frequencies enter into the system. So the same experiment done in another way. So this sinusoidal wave which you're seeing here, it is not a time varying signal, it's a space varying signal. So when this is sent into an incoherent system, denoted by IC, and coherent imaging system, you can see that incoherent imaging system has a better response. So consequently, they also have super resolution. Okay, so now we know the basics of how coherent imaging systems and incoherent imaging systems work. So with that knowledge, let us move forward to understanding frontal incoherent correlation holography, or FINCH. Okay, so FINCH was invented by Professor Joseph Rosen from Ben Gurion University. He was my postdoctoral advisor during my stay. And Professor Gary Brooker. So Professor Gary Brooker is basically, he's a biologist, whereas Professor Rosen is an electrical engineer and optical scientist. So they both invented this concept of frontal incoherent correlation holography. Of course, holography is not very new to you. In general, I mean, also in most of the textbooks, how hologram is recorded. We have a laser which is shined on the object, and the light diffracted from the object is interfered with the reference wave. And this reference wave is usually a plane wave with no information of the object. But we have already established that such a configuration will not work for incoherent imaging systems because of lack of spatial coherence. But we also know that in the case of single point, there is no difference between a coherent and incoherent imaging system. So with that, let us try to see if we can create a holographic system with incoherent sources. So a single point is coherent with respect to itself. So with that concept, so this FINCH was developed. So every point of this object is incident on the spatial light modulator. And on the spatial light modulator, there are two lenses displayed. So the same point, the light from the same point is divided into two, and an interference pattern is formed between these two. So this is very different from how a usual hologram is recorded. So this hologram is also called as self-interference hologram because a point is interfered with itself. And now the same concept can be applied to any number of points, and you can transfer 3D information into this hologram. But as we know, this is an inline configuration. When we reconstruct this hologram, there is always this twin image and bias terms. So it is necessary to create multiple camera recordings to remove this unwanted noises. So what Professor Rosen and Gary Brooker did was, they took a random phase mask and then they binarized it like this. And then they incorporate two lenses in this way. So they multiplied the lens function to this and second lens to the remaining area. So they created a bifocal lens, and they created phase shift. So they changed one lens with respect to the other in steps of 120 degrees. And this is how it looks like. So this is the binary phase mask, and these are the phase shifted phase masks, and this is the test object, and this is how the hologram looks like, an incoherent self-interference hologram. This is how it looks like. And these three holograms are projected into complex space to create a complex hologram, and this is the amplitude and phase of the complex hologram. And when it is reconstructed, we get this result. And as you can see, this result is not very close to the test object. It is because of the use of random phase mask. This random phase mask helps in multiplexing two functions, but also creates this kind of noises. But these kinds of noises are only present when the object is a complicated object like this. But if the object is a sparse object, like the points are separated from one another, then in that case, this effect is not dominant. So Professor Rosen and Brooker, they went on to demonstrate this on a fluorescent microscope. As you know, fluorescence, this is not a coherent light. So it is impossible to create a 3D imaging system using conventional holography. So FINCH came to its rescue. So you can see this is the configuration of a fluorescent microscope. There is an arc lamp, which is the excitation source, which excites this sample, and the excited wavelength goes into this. And on the SLM, we have the twin focal lenses, and then the hologram is recorded in the CCD. Now let us see how it is different from a direct imaging system or a conventional imaging system. In a conventional imaging system, when there are 2 points which are separated by a distance, and there is a sensor here, we can at a time capture only the image of one point. You can see this image is formed clearly, but the other image or the image of the other object, it looks blurred. So in order to record the other image, it is necessary to either move the sensor towards the object or to change the location of the lens. But it's kind of complicated when the object consists of, say, hundreds of planes. But with Finch, you can see what we obtain is a Finch hologram. And by taking this Finch hologram into the computer, it is possible to do digital refocusing. It doesn't matter whether you have 100 planes or 1000 planes. So this digital refocusing can be achieved. And these are some of the results they obtained. This is for plane 1, this is for plane 2. They also tested it on different types of biological samples, and it was published in Nature Photonics in 2008. Okay, so now using Finch, we can have a 3D fluorescent microscope. But later, they found that even more convincing reason to use Finch. This definitely is an advantage, but later they found that Finch also exhibited super resolution. Okay, so that's what I'm going to explain to you next. So what is Lagrange invariant condition and how to break it to achieve super resolution? Okay, so this Lagrange invariant condition, it is also called as Smith-Helmholtz formula. There are different ways to explain this formula, but I prefer to go with the magnification method. So let us say there are 2 points, and this x1 is the size of the point, and y1 is the spacing between the 2 points. In a linear imaging system, this magnifications, this mx, which is x2 by x1, which is the magnification of which is the ratio between the image and object, and this is the ratio between the spacing between the images and spacing between the object. And in a linear imaging system, as we all know, this has to be equal. Otherwise, the image is not a clear representation of the object. In usual cases, mx is equal to my. Then we say Lagrange invariant condition is satisfied. But then, when mx is not equal to my, this Lagrange invariant condition is not satisfied. And let us consider the third case. When my exceeds mx, then it seems that the spacing between the 2 points is more than the magnification of the single point. Then we can call that as super resolution. So this kind of super resolution is completely different from the usual super resolution microscopes. Let us take structured illumination. Let us take a storm. So all these methods, they don't exhibit nonlinear super resolution, but only Finch or incoherent imaging system in this configuration exhibits nonlinear super resolution. So I have created a figure to explain this using geometry. So there are 2 points, O1 and O2. So these are the 2 images formed by the 2 lenses. And if you see this I1 and I11, so the fringe frequency here is, it just involves the quadratic phase from the 2 points. But here, I2 and I22, along with the quadratic phases, there is linear phase. And this linear phase, when they are in opposite direction, they add up, increasing the fringe frequency to twice. So consequently, the magnification, that mx, is actually half of my. So this is the maximum we can achieve. So what it does to the modulation transfer function? We have already known that this modulation transfer function of a regular incoherent imaging system is like this. But so this is what happens in a regular incoherent imaging system, whereas in Finch, it becomes like this. So the resolving power of Finch is actually twice as much as that of a coherent imaging system, or 1.5 times approximately than that of regular incoherent imaging system. And these are the 2 images which was obtained for regular imaging system, this for Finch. So now Finch has 3D imaging capability. In addition to that, it also can exhibit super resolution. So this made Finch a very attractive tool for various applications. And these are some of the results obtained using Finch. And this is the wide field fluorescent microscopy. And you can see this from Finch. Finch has better resolving power, and same thing with magnified versions of some of the points. And this is the pollen grain, I think, pollen sample. And definitely you can see a super resolution here. And this is the fundic stomach fluorescence image. So this made Finch a very, valuable tool. And Professor Rosen and Brucker, they went on to create a company called Cell Optic, which creates 3D fluorescent microscopes based on Finch. Okay, so we have already explained that we already know that the random multiplexing creates random noise. So in order to solve this problem, they came up with this concept of polarization multiplexing. So before the light enters the special light modulator, they inserted a polarizer P1, But instead of orienting it along the active axis of the SLM, what they did was they oriented at 45 degrees with respect to the active axis of SLM. So only part of the light was modulated, and the remaining part remained unmodulated. And a second polarizer was introduced to create interference between these two beams. So now the random noise was also, avoided. Okay, so now let us go to evolution of Finch over the years. So how Finch evolved. Okay, so they solved this random multiplexing problem. Now we can create Finch holograms and reconstructions without any noise, but still Finch requires at least 3 camera shots. And as the users, not the optical imaging scientists, but the users, the end users, they don't prefer taking multiple camera shots. So it is always better to record a single camera shot, and if you can get complete 3D information of the object, then it becomes even more valuable. So this attempts made by Japanese researchers. I think this was done by Dr. Nobukawa. So he created a multiplexed hologram, and he collected all the temporal shots with some spatial separation directly on the sensor. So you can see these are the 4 phase shifted masks, and these are the holograms. So in a single camera shot, he was able to get all the 4 shots needed, and he demonstrated 3D imaging. But the problem was that in this process, he lost field of view, because you can see this sensor cannot record larger holograms, which directly affects the field of view of the imaging system. So the second attempt was made by Professor Matoba and also Professor Tahara. So in this case, they used a slit with grating to create this interference, but you can see the reconstruction is not very good. And later, Tahara introduced the concept of polarization multiplexing. So he used a polarizer, and then he used here this 4-pole camera, which is every pixel has a polarization orientation of 45 degree relative to the other pixel. So these are the different phase shifts he can obtain from a single camera shot. And once again, the problem was, in this case, the problem was higher noise. Okay. So these are some of the interesting applications with Finch. As I already mentioned, Finch has this interesting profile that MTF is flat. And so what we did was, in the case of structured illumination, as you know, this different types of grating patterns are incident on the object, and the multiple holograms are recorded, or intensity patterns are recorded, and they are combined to create super resolution. So initially, the imaging system has a resolution defined by this MTF, but by introducing spatial frequencies like grating structures incident on the object and recording these corresponding holograms and combining them with this, so it is possible to create or extend MTF in this way. So this is the extended region. But this method is not, it's definitely a super resolution method, but it is not fully effective, because its full capability has not been used. Because you can see these regions, these V-type regions. So these are the regions where the spatial frequency suffers some loss. Even though we have the spatial frequencies, the gain is not to the maximum value. But if this regular imaging system is replaced with Finch, you can see that this uniform profile enhances the resolving power even further. So this is the demonstration we made in 2016. So this is the result with structured illumination and regular imaging system. And this is the case with Finch and structured illumination method. You can see we were able to perceive features which are not visible in the previous study. And later, we found a way to use Finch as a resolution booster. Of course, this is also a resolution booster. But here, this is a Finch system. So we introduced a scattering mask between the object and the SLM. And this scattering mask, what it does, the spatial frequencies from this object, they are collected only within the numerical aperture defined by the physical aperture. But now by introducing this scattering mask, it is possible to scatter these higher spatial frequencies back into the system. So in this way, it is possible to increase the resolving power. So the first image which you're seeing here, it is the case with the direct imaging system, not Finch. And this A2, it is obtained with Finch, but no scattering mask. You can see the images, it's not resolved. But then as we increased the scattering ratio of this mask gradually, this sigma represents the scattering ratio, 0.074, 0.15. You can see that as we increase the scattering ratio, the resolving power of the system improves. And you can also notice this visibility graph, which clearly indicates the improvement in resolving power. And another drawback, I mean, of course, there is no free lunch. So whenever we try to increase or improve one characteristics, the other characteristic, they get affected. So in this case, when we increase the scattering ratio, we improve the resolving power, but we lose the field of view. You can see that gradually the field of view is decreased. And so in using this method, we were able to demonstrate a resolution enhancement of around, say, 5 times. So in comparison to coherent imaging system, the enhancement is around, say, 10 times. So just imagine seeing a resolution enhancement where your microscope used to resolve only 1 micrometer, now it can resolve until 100 nanometer. So that's what the application. Okay, so now single camera shot Finch. Okay, so with all these advancements, also Finch, the original problem of Finch, where multiple camera shots were needed in order to record a hologram or reconstruct 3D information, was not solved. Okay, so the problem of not solving this, one of the main problems was that people were looking at this problem in the same way. So we thought, okay, why should we look at this problem in this way? Why not we look at this problem in a different way? Let us recall this convolution correlation approaches, which I explained before. And I would like to explain this again with even better, experiment. I believe you all have used a vending machine at some point in your life. If you were in Japan, then I think you have the opportunity to use vending even more often. You can get hot noodles. You can get almost anything from a vending machine. Now let us assume that you have a vending machine, but you don't know what the vending machine will give you. We know that we will make an assumption that you know that money is made up of a fundamental building block, which is $1. So everything has to be in multiples of $1. $1, $2, $3, $100, but not 1.5 or 0.5. Let us make this assumption and let us try to understand this vending machine. So how do we understand this? So let us insert this $1 and see what it does. Okay, so it gives an output, which is a can of Coke, let us say. So now we know that when we insert $1 into the vending machine, it gives us a single can of a drink of Coke. So this explains, so this concept also called as the PSF, point spread function. It is also called as the impulse response in time domain and point spread function mostly in spatial domain. So the first experiment is done. So when we insert $1, we get 1 can of Coke. So we need to understand whether the system is linear. So we do the next experiment. So we send $2. Okay, so we get 2 cans of Coke. So we know that the system is linear. So there is a 1-to-1 correspondence. So when we send $1, we get 1 can, and when there are $2, we get 2 cans of Coke. So now, if we get this output, we can easily predict that what is the input is. So we definitely know that $3 have been inserted into the system. Okay, so the first step is called as the PSF, or the impulse response, and the second step is called as convolution, and the third step is called as correlation. And in this experiment, you can notice that there is no space or time domain. But now, as we move to the next slide, I'm going to introduce space coordinate. Okay, so same experiment. There is like a magic box or like a black box. I don't know what this box does. So we send a single fundamental unit, which is a point, and then this system generates this. So this is the PSF of the system. And now, as I said, we are going to introduce space coordinate. So when we do that, so 1-to-1 correspondence occurs, except that it is also dependent on space. So 4 points creates 4 such patterns. And so in this case, it is kind of easy. So, these are 4 PSFs. So you can easily say, okay, so there are 4 points. But what if these points are very close to one another? So in that case, it is kind of complicated to reconstruct the information from this output. So for that, we do something known as this pattern recognition approach. So we have this PSF, that is this can of Coke. So if we have this monitor and scan this PSF over this output, and this monitor beeps or creates a peak whenever there is a pattern matching. So if we do this, then we can reconstruct the information. So this process is called as correlation. So let us use this idea to finch. So that's what we did. Okay, before that, this is some mathematics. So once again, we have these 3 coins or PSF, and this gets convolved to maybe a can of Coke, and then this is the output. This process is called convolution. Mathematically, it can be expressed like this: Fourier transform of matrix 1, Fourier transform of matrix 2. We do a product, and then if we take an inverse Fourier transform, then it is equivalent to convolution. And the last step, which we correlation, it can be done like this. So we have this output. If we correlate this with either the PSF or this, then we get other matrix information. So once again, the same procedure: Fourier transform of matrix 1, Fourier transform of matrix 2, and this bar symbol indicates complex conjugate. And if it is a real matrix, then you have to just flip it. And multiplication followed by inverse Fourier transform. So this is the approach we used in finch to achieve a single shot. So in finch, when there is a single point, this is what is the output. And when there are more than one point, in this case 2 points, you can see there are 2 such PSFs. And whenever there is an overlap, there is an intensity addition. Exactly same as the way incoherent imaging system works. Now we know this. If we know this PSF, then using this correlation approach, we can reconstruct the object information. So that's what we tried here in this work. Okay, sorry. But as you know, finch is a 3D imaging system, holographic system. So we need to know the PSF not only at just one plane, we need to record it at multiple planes. So what we did was we created a library, PSF library, or more correctly, PSH library, because it is not point spread function, it is point spread hologram. So we created this library and correlated every element of this library to the object function, and we can achieve 3D imaging capability. So these are some of the results. This is and also we try to avoid the special rate modulator, which is more expensive, and we fabricated this device using electron beam lithography. This is the bifocal lens, and these are the imaging results of a standard test object in USAF resolution target. And this is the wing of an insect we imaged using finch. This is the result we obtained from direct imaging, and this is the result from finch. You can see that with finch, the resolution is much better than regular imaging. And these are with, and this result was to show super resolution. This is the one with direct imaging, and this is the result with finch. And you can see that the resolving power is significantly better than direct imaging. And this is the 3D imaging result. We recorded the PSF at 2 planes, and we reconstructed the object information at the 2 planes. Okay, so now we are almost at the end of the talk. Okay, so the conclusion is finch is a super resolution imaging technique with a resolution enhancement of about 1.5 times compared to a direct imaging system. And finch can also be used as a resolution booster to work with other existing super resolution techniques so that we can multiply resolving powers. And finch has already entered the commercialization step, and it is available as finch and cinch at Cell Optic. And finch still requires at least 3 camera shots to reconstruct the object information. So it requires a SLM, but single shot has been achieved using this novel pattern recognition approach. And recently, we also developed a new algorithm called as Lucy-Richardson-Rosen algorithm. Lucy-Richardson is a very widely used algorithm for deblurring object information recorded using microscopes, telescopes, or also even regular cameras. So we combined one of the algorithms developed by Rosen with Lucy-Richardson, and we created this Lucy-Richardson-Rosen algorithm. So with that, we were able to even achieve single shot much better. So this is the result with Lucy-Richardson-Rosen algorithm. I have 2 videos which was created for our work in Australian synchrotron. So we used to develop holography and imaging techniques at the Australian synchrotron for the infrared beamline. And the Lucy-Richardson-Rosen algorithm was applied to one of such cases. So I'll show you a video. Okay. Okay, so the first window shows the usual Lucy-Richardson algorithm, and the second one shows the outcome with Lucy-Richardson algorithm. You can see that the convergence of Lucy-Richardson-Rosen is quite rapid compared to Lucy-Richardson, and also the estimation is significantly better. And this is for a very simple object, so you can, maybe the difference is not very clear, but when we apply it to biochemical samples, like silk samples, like wings of insects, maybe some tissue, so then we identified that the LR array had a very significant improvement over Lucy-Richardson algorithm. And currently, our group and my postdoctoral advisor and currently my collaborator, we are looking into artificial intelligence-based reconstruction possibilities to achieve single shot. Because even though we claim that it is cross, it is not ideally cross. There are some issues. We are trying to figure out this problem using deep learning approaches. Okay, and these are some of the notable works we did with Finch, and it was highlighted in the cover page of Chinese Optics Letters. And this was from Optoelectronic Advances. We won a research award for this work. And this was, say, highlighted in physics.org. This was the work which we did it in the Australian synchrotron. Okay, so we have many funded projects. Our project is funded by European Union, and it's worth around, say, 2.5 million euros. And we have multiple positions for PhD, master's, and bachelor thesis. Of course, the master's and bachelor is for Estonian students, but we have PhD openings. And one of the PhD opening will be announced on the 15th of November. It's a dual PhD program between Estonia and Israel. The students spend 2 years here and 2 years in Ben Gurion University. And one more position will be, open next year. Okay, so thank you very much for your patience. And once again, thank you very much for the opportunity. So I welcome questions, comments.